During the next couple of lectures, we will study quantization, one of the simplest and most general ideas in lossy compression. In many lossy compression applications, it is required to represent each source output using one of a small number of code words. The number of possible distinct source output values is generally much larger than the number of code words used to represent them. This process of representing a large, possibly infinite set of values with a much smaller set is called quantization. The device which achieves this quantization is called quantizer. Consider a source that generates numbers between -5 and +5. A simple quantization scheme would be to represent each output of the source with the integer value closest to it. For example, if the source output is -2.4251, we would represent it as -2, and if the source output is 4.2452, we would represent it as 4. This approach reduces the size of the alphabet required to represent the source output. The infinite number of values between -5 and +5 are represented with a set that contains only 11 values: -5, -4, -3, -2, -1. At the same time, we have also forever lost the original value. If we are told that the reconstruction value is 2, we cannot tell whether source output was 1.92 or 2.2 or 2.14 or any other of an infinite set of values. In other words, we have lost some information. This loss of information is the reason for the use of the word lossy in many lossy compression schemes. The set of inputs and outputs of a quantizer can be scalars or vectors. If they are scalars, we call the quantizer as scalar quantizer, and if they are vectors, we call the quantizers vector quantizers. Let us begin our study with scalar quantizers. Though the process of quantization is very simple, however, the design of the quantizer will have a significant impact on the amount of compression that can be obtained and the loss incurred in a lossy compression scheme. Let us examine the issues related to the design of quantizers in little more depth. In practice, the quantizer consists of two mappings: an encoder mapping and a decoder mapping. The task of an encoder is to divide the range of values that the source generates into a number of intervals. Each interval is represented by a distinct code word. The encoder represents all the source outputs that fall into a particular interval by the code word representing that interval. Now, as there could be many, possibly infinitely many distinct sample values that can fall in any given interval, the encoder mapping is irreversible. Knowing the code only tells us the interval to which the sample value belongs. It does not tell which of many values in the interval is the actual sample value. When the sample value comes from an analog source, the encoder is called an analog to digital converter. Now, the task of a decoder is to generate a reconstruction value. Because a code word represents the entire interval and there is no way of knowing which value in the interval was actually generated by the source, the decoder generates a value that in some sense best represents all the values in the interval. Now, to do this, we can use the information about the distribution of the input in the interval to obtain a representative value. For time being, let us simply use the midpoint of the interval as the representative value generated by the decoder. So, if the reconstruction is analog, the decoder is often referred to as digital to analog converter. A decoder mapping corresponding to the 3-bit encoder discussed earlier is shown here. For the input code word 000, the output reconstructed value is minus 3.5, and for the input code word 100, the output of the decoder is 0.5. So, construction of the intervals, their location, etc., can be viewed as part of the design of an encoder. Selection of reconstruction value is part of the design of a decoder. However, the fidelity or accuracy of the reconstruction depends on both the intervals and the reconstruction values. We call this encoder decoder pair as a quantizer. In summary, to specify a quantizer, we need to know how to divide the input range into intervals, then assign code words to these intervals, and finally find representation or output values for these intervals. We need to do all this while satisfying distortion and rate criteria. Now, distortion is defined as the average squared difference between the quantizer input and output. We call this mean squared quantization error, in short as MSQE, and this is denoted by sigma squared q. Similarly, the rate of the quantizer is the average number of bits required to represent a single quantizer output. Now, our goal should be to get the lowest distortion for a given rate or the lowest rate for a given distortion. Now, this quantizer design problem can be posed in precise terms as follows. Let us assume an input modeled by a random variable x with probability density function, that is PDF, given by P subscript capital X x. Now, the design problem is to quantize the source with L intervals, that is, we have to specify L plus 1 endpoints for the intervals and a representative value for each of the intervals. Now, the endpoints of the intervals are known as boundaries, while the representative values are known as reconstruction levels. So, let us denote the decision boundaries by Bj. J goes from 0 to L, the reconstruction levels by Yj, J is equal to 1 to L, and the quantization operation by Q. Then Qx is equal to Yj if and only if x lies in the interval specified as follows. Now, the mean squared quantization error is given by integral from minus infinity to plus infinity x minus q x squared PDF of the random variable x, and this can be rewritten as follows: summation over L intervals with quantization error for a particular interval given by the integral. The difference between the quantizer input x and output y is equal to q x is referred to as the quantization error. Or it is also known as quantization distortion, or more popularly known as quantization noise. So, the quantization process can be modeled as an additive noise process as shown here. We have a quantizer input and quantization noise gets added to it to give the quantizer output. This is additive noise model of a quantizer. Now, if we use fixed length binary code words to represent the quantizer output, then the size of the output alphabet immediately specifies the rate. So, if the number of quantizer outputs is L, then the rate is given by R is equal to the next largest integer of log to the base 2 of L. So, if L is equal to 16, then R is equal to 4. Therefore, the quantizer design problem can be posed as follows. Given an input PDF and the number of levels L in the quantizer, the problem is to determine the decision boundaries, that is B j, and the reconstruction levels, that is Y j, so as to minimize the mean square quantization error given by the following expression. Now, however, if we are allowed to use variable length code words, codes such as Huffman codes or arithmetic codes along with the size of the alphabet, the selection of the decision boundaries will also affect the rate of the quantizer. However, if we are allowed to use variable length codes such as Huffman codes or arithmetic code along with the size of the alphabet, the selection of the decision boundaries will also affect the rate of the quantizer. For example, let us look at the code weight assignment for L equal to 8 quantizer. According to this code word assignment, if the output Y5 occurs, we use 2 bits to encode it, while if the output Y2 occurs, we need 4 bits to encode it. Now, the average rate will depend on how often we have to encode Y5 versus how often we have to encode Y2. This implies that the average rate will depend on the probability of occurrence of the outputs. So, if Lj denotes the length of the code word corresponding to the output yj and probability yj is the probability of occurrence of yj, then the rate is given by however, the probabilities Pyj depend on the decision boundaries Bj. For example, the probability of Yj occurring is given by therefore, the rate is a function of the decision boundaries and is given by the expression so, what follows from the discussions and this equation that for a given source input, the partitions we select and the representation for this partitions will determine the distortion incurred during the quantization process. And the partitions we select and the binary codes for the partitions will determine the rate for the quantizer. Thus, the problem of finding the optimum partition codes and representation levels are all linked. In light of this information, we can restate a problem statement as follows. Given a distortion constraint, determine the decision boundaries, reconstruction levels and binary codes that minimize the rate given by this expression while satisfying the above distortion constraint. Or the same problem can be posed as follows. Given a rate constraint, determine the decision boundaries, reconstruction levels and binary codes that minimize the distortion given by this expression while satisfying the above rate distortion constraint. Now, this problem statements of quantizer design, while more general than our initial statement, is also substantially more complex. However, in practical applications, there are situations in which we can simplify the problem. We often use fixed length code words to encode the quantizer output. In this case, the rate is simply the number of bits used to encode each output, and we can use our initial statement of the quantizer design problem. So, let us begin our study of quantizer design problem by looking at the simpler version and then move over to tackle more complex version. So, the simplest type of quantizer is the uniform quantizer. All intervals in uniform quantizers are of the same size except possibly for the two outer intervals. So, a uniform quantizer has the following properties. The decision boundaries are spaced evenly, the reconstruction levels are also spaced evenly with the same spacing as the decision boundaries. In the inner intervals, they are the midpoints of the intervals. This constant spacing is usually referred to as the step size, and it is denoted by delta. Now, the mapping for the quantizer for the 3-bit encoder pair discussed earlier can be represented by the input output map shown here. This is an example of a uniform quantizer with delta equal to 1. It does not have 0 as one of its representation level. Such a quantizer is called a mid-rise quantizer. An alternative uniform quantizer could be the one shown here. This is called a mid-thread quantizer. Usually, we use a mid-rise quantizer if number of construction levels, that is L, is equal to even, and we use a mid-thread quantizer if the number of reconstruction level is odd. Now, for our discussion, we will assume mid-rise quantizer. We will also assume that the input PDF is symmetric around the origin, and we also assume that the quantizer is also symmetric. This will simplify our discussions. Now, given all these assumptions, the design of a uniform quantizer consists of finding the step size delta that minimizes the distortion for a given input process and number of decision levels L. So, we start our study of quantizer design with the simplest of all cases. Let us consider design of an L level uniform quantizer for an input that has uniform probability density function in the interval minus x max to plus x max. Now, this implies that we need to divide the input range minus x max to plus x max into L equally sized intervals, and in this case the step size delta is given by 2 x max upon L. Now, if we assume that the reconstruction level is the midpoint of the boundaries, then for this assumption the distortion becomes we assume L is even, and since the PDF of the input is uniform, we can write as 1 by 2 x max. The jth interval is given by these boundaries. Now, if we evaluate this integral, we find that the mean square quantization error is equal to delta squared by 12. Now, this same result can be more easily obtained as follows. The quantization error Q is given by x minus q x, and if we plot this quantization error for a uniform mid-rise quantizer for L equal to 8 with input in the interval minus x max to x max and uniform PDF, we get the following plot. Therefore, the quantization error lies in the interval minus delta by 2 to plus delta by 2. Now, as the input is of uniform PDF, it is not difficult to show that the quantization error Q is also uniform over this interval. Thus, the mean square quantization error is nothing but the second moment of a random variable with uniform PDF in the interval minus delta by 2 to plus delta by 2. And if we assume this, we get mean square quantization error as 1 by delta, which is the PDF of uniform random variable q integrated over minus delta by 2 to plus delta by 2 of q squared dq, and this is equal to delta squared by 12. Let us also calculate the signal to quantization noise ratio, which we will simply denote as signal to noise ratio. This is actually signal to quantization noise ratio, but for simplicity we will denote it as SNR Q. Now, the signal variance that is sigma squared x for a uniform random variable x, which takes on values in the interval minus x max to plus x max, can be shown to equal as x max upon and we also know that delta is equal to twice x max upon L. Now, for the case where we have used a fixed line codes with each code word being made up of m bits, the number of code words or the number of reconstruction level L is equal to 2 raised to m. So, given this, we can calculate signal to noise ratio, which is, to repeat again, signal to quantization noise ratio in dB, that is in decibels, is equal to 10 log to the base 10 of signal variance divided by quantization noise variance. This can be rewritten as 10 log 10. Signal variance is equal to twice x max squared divided by 12, and quantization noise variance is equal to sigma squared by 12 . This can be rewritten as delta is equal to twice x max upon L. So, this can be simplified as and further simplified which is equal to 6.02 m dB. Now, what this equation says, that for every additional bit in the quantizer, we get an increase in the signal to noise ratio of approximately 6 dB. Now, this is a well known result and is often used to get an indication of the maximum gain available if we increase the rate. Now, let us solve a few simple examples based on this concept. Let us say that the maximum acceptable quantization error in the sample amplitude is 0.5% of the peak amplitude. Let us assume that the quantized samples are binary coded. And it is desired that we determine the length of a code word for a fixed length code. Now, the solution to this problem is as follows. So, we assume that the quantizer is uniform. So, maximum quantization error in terms of step size delta is delta by 2. Now, we also know that delta is equal to 2 x max by L for a uniform quantizer. Therefore, delta by 2 is equal to x max by L, and this is equal to 0.5% of the peak amplitude, that is 0.5 x max upon 100, which implies that L is equal to 200. Now, assuming fixed length code and binary coding, implies that L must be power of 2. Hence, the next higher value of L, that is the power of 2, is L is equal to 256, and therefore, m is equal to log to the base 2 of 256 is equal to 8 bits per sample. So, this is the desired solution, and the signal to noise ratio, that is quantization noise in terms of dB, is equal to 6.02 multiplied by 8 is equal to 48.16 dB, assuming that the input PDF is uniform. Let us take another example. Let us determine the step size, that is delta, given we want uniform quantization and the input has uniform PDF with variance equal to 1, and let us assume that L is equal to 4. Now, the solution is as follows. If the input range is minus x max to plus x max, and if the input is uniform PDF, then its variance is 2 x max squared by 12, which is equal to x max squared by 3, and this is equal to 1. Therefore, it implies x max is equal to 1.732. Therefore, for L equal to 4, we get the step size delta equal to twice x max by L is equal to 0.866. Again, signal to noise ratio, that is quantization noise in dB for this case is equal to 6.02 multiplied by 4 is equal to 24.08. Now, it is important to remember that we derived the signal to noise ratio, that is quantization noise dB equal to 6.02 m under certain assumptions about the input. If these assumptions are not true, then this result will also not hold. Now, quite often the sources we deal with does not have a uniform PDF, and we still want to have the simplicity of a uniform quantizer. In these cases, even if the inputs are bounded, then simply by dividing the input range by the number of reconstruction level will not provide a very good quantizer design, and this approach will become practically impossible when we model the sources that have unbounded PDF such as Gaussian PDF. Now, in the next class, we will examine design of a uniform quantizer for non-uniform sources.